Hi to everybody. In this lecture video, we are going to be focusing on chapter 25. And chapter 25 is about electric potential. Now, after completing this chapter, you will be able to derive equations for the difference in potential energy and the potential difference between 2 points. Now, for the sake of terminology, we are going to be using U to denote the potential energy. Potential energy. And then we are going to be using V to denote potential. Potential. The electric potential is just denoted by V, while the potential energy is just denoted by U. Now the difference in potential or change in potential difference will just be denoted by this, and the change in potential or potential difference is just denoted by that. So these two are very important, and I want you to always know the difference between the potential energy and the just potential. Now, the second thing that you will be able to do is to define the potential difference between 2 points, the potential at the point and the volt and the electron volt. And you will also be in a position to derive an expression for the potential difference between 2 points in uniform electric field. And you will also be able to find the potential at any point due to a group of point charges. And you will also be able to define the electric potential energy due to group of point charges. And you will also be able to solve the problems on the above aspects. Now, let us just start with potential energy. Now, from chapter 23, we know that when a certain test charge of a certain magnitude Q naught is placed in an electric field, it will just experience this force. It will just experience this force. Now, that force is conservative force. Now, if the test charge is moved in the field by some external agent, the work done by the field is the negative of the work done by the external agent. Now, the ds is just a small displacement vector that is orientated tangent to the path through space. Now, the work done by the electric field is just given by F dot ds. You know from your high school that the work done, you used to write this like the work done is just given by F times S or D. Now, in such cases, you don't see the cosine of an angle there because the force is pointing in the same direction as the displacement. So as a result, the angle between 2 point vectors which are pointing in the same direction is just 0. That is why you end up with this work is just force multiplied by displacement. Now, we already know what is the force. Now, if we plug the value of a force, this is what we are going to have. Now, as this work is done by the field, the potential energy, which is U, of the charge field system is changed by this. The change in potential energy is therefore given by this equation here. Now, this negative here is for the fact that this work is done by the field, as I've explained in my previous slide. Right. Now, for a finite displacement of the charge from point A to B, then the change in potential energy can just be given by the potential at B minus the potential at A by this integral, where this integral are taken from A to B. Now, E dot ds. Right. Now, because the force is conservative, the line integral does not depend on the path taken by the charge. It is just depending on from point A to just point B, not the path taken to arrive to point B from point A. Now, this is the change in potential energy of the system. Right. Let us also talk about the electric potential. Electric potential, that is your V. Now, the potential energy per unit charge U divided by Q naught is given as the electric potential. Now the potential is a characteristics of the field only, while the potential energy, which is U, is characteristic of the charge field system. Now the potential is independent of the value of Q naught. The potential has a value at every point in an electric field. Now the potential or the electric potential is just given by this equation here, right? Now the potential is a scalar because since or energy is a scalar. Now as charge particles move in an electric field, it experiences a change in potential, and that change in potential is just given by this equation, taking into account that the change in U is just given by Q naught minus Q naught, the integral of A to D. Now that Q naught that is coming from the change in U from the previous slide will cancel with this one. Now we end up with the change in potential, or the potential difference is just given by this equation. Right. Now the difference in potential is the meaningful quantity. Now we often take the value of the potential to be zero at some point which is convenient in a field. Now electric potential is a scalar characteristics of an electric field independent of any charge that may be placed in that field. Now if you assume a charge moves in an electric field without any change in its kinetic energy, the work performed on the charge is just given by this equation here. This is the equation that you know from your high school. Now the work done is nothing else but it's just a change in potential energy. Now the units of the potential or electric potential is just V, and it is just termed the volt. Now 1 volt is equivalent to 1 joules per coulomb. It takes 1 joules of work to move 1 coulomb charge through a potential difference of 1 volt. Now in addition, from the previous chapter, we know that the electric field units is just given by newtons per coulomb. Now in this case, 1 newtons per coulomb is just given by 1 volts per meter. Now this implies that we can also interpret the electric field as a measure of the rate of change with position of the electric potential. Now I will also have to prove this to you a little bit later, that the electric field can also be written in terms of the gradient of the potential. Now electron volts, another units which is often used in other fields of physics such as atomic physics and nuclear physics, is the electron volts. Now 1 electron volt is defined as the energy a charge field system gains or loses when a charge of a certain magnitude or of a certain magnitude E, which is an electron or a proton, is moved through a potential difference of 1 volt. Now 1 electron volts is just given as 1.60 times 10 to the power minus 19 joules. Now let us just do the following quick quiz. In this figure here, 2 points A and B are located within a region in which there is an electric field. How will you describe the potential difference, the potential difference between a point A and B? The potential difference is just from point A to B. Now from the previous equations that we have derived, that the change in V is just equals to minus integral E dot ds. Now in this case, this is a dot product between 2 vectors, and the electric field is always pointing in the same direction as the displacement. Now do you see that the dot product between 2 vectors will always give me the scalar quantity? Then I can write it in terms of this ds. Now, because the electric field is a constant, I will just have E outside the integral, but the integral ds is nothing else but it's just the distance that the charge will move. And if I call that distance d, then this is what you are going to have. Right, now do you see the answer will always be negative? That is the correct answer for this quick quiz is going to be number B. Right, now the part 2 of the question is a negative charge is placed in at A and then move to B. How will you describe the change in potential energy? Now the change in potential energy, it means U of the charge field system for this process. Now I just want to remind you about the equation of the change in potential energy. The change in potential energy, which is just U, is just given by negative Q naught integral, the integral of E dot ds. Now in this case, as we can just quickly see that this negative is actually coming from the equation itself. Now you've got minus, and now the charge is negative in this case. Now you are going to have minus Q naught, and then everything will just be the same. What I'm trying to say here is this is going to be negative multiplied by negative, then you will end up with positive, and then Q naught, and then all other terms. So now the answer, which is correct for this quick quiz, is then obviously number A. Right. Now, what does that mean? So if a negative test charge is moved through a negative potential difference, because we've just calculated the, we have also seen that the potential is negative from part 1 of this question. Now the change in potential energy is positive. This is what we've just done. Now the work done must to move the charge in the direction opposite to electric force on it. Right. Now potential difference in a uniform field. Now the potential difference is just given by this equation here, and as I've shown you that if the integral from A to B, if the path from A to B is just given as d, the integral from A to B ds is just d. As a result, this is what you are going to have as your change in potential. Now let us just do this a little bit further. Now we are seeing that the change in potential is just given by this equation here. The change in potential is just given by minus ed. Now if we rearrange this equation, to find the electric field, this is just what we are going to have, change in V divided by D. Now in terms of the units, you can just be able to see that the units for this is just going to be volts per meter. Now, as I've said earlier on, that we knew from the previous chapter that the electric field is just given by that, and now in that case, the units for the electric field was just given by newtons per coulomb. Now that is why I said earlier on, the electric field can also be determined in terms of these two units, and they are both equal or equivalent. Right. Now the negative sign indicates that the electric potential at point B is lower than at point A. What does that mean? It means that the further you go to the field, the lesser the potential you will experience, or the charge will experience that positive charge. Now, electric field lines always point in the direction of decreasing in electric potential. Right. Now, for the sake of understanding, say you are placing a certain charge, or it can be positive or negative. For example, in this case, let us consider if this charge is positive. You want this charge to move from point A to B. And from what we have just discussed now, we know that the potential at B is always less than the potential at B because of the direction of the electric field. Now, let me just hang on. For me, I just want to show you the the simulation for this, so that I can just easily summarize everything in just a small time. Now I just want to go and get the file that I want to be in the right place. Right, thank you. Now this is what I wanted to show you. Now here I am going to be comparing the electric field system and the gravitational field system. So now electric field system is the one with dealing with the charges and then the electric field. For example, the electric field is going in this direction and you've got the positive charge there. While the gravitational field system is the system which is dealing with the gravitational field, which is G, and then it is dealing with the mass. So as a result, for the gravitational field system, I can be able to change the mass of my object. While in my electric field system, I can be able to change the magnitude of this charge. The magnitude of this charge and the polarity of the charge. I can make it positive, I can make it negative, I can also make it I can also make that particle to be neutral, and I can also be able to vary the electric field. And what I want you to also see is the fact that you've got the potential energy and you also have the kinetic energy. Now, the moment I release these objects, this is what is going to happen. Do you see when the object is moving, the potential energy is lost and then the kinetic energy is being gained. Now, the moment the kinetic energy, the potential energy is lost, the kinetic energy, the same amount of the energy which is lost by the potential is the amount which is being gained by the kinetic energy. Now, for the sake of clarity, I can change the mass of the object in the gravitational field system, and I can also change the electric field in this system. Now, if I release, this is what you are going to see. Now, as you can see, the charge is now a little bit faster compared to when the electric field was a little bit lower. Now, the other thing that I want to show you is, let me just change the charge to be negative. And I want to pause a little bit and then give you a chance to think about it. Now the electric field is going in this direction. What do you think will happen to this negative charge? Right. When I release, there's nothing that is going to happen to this negative charge because the electric field is going in this direction. That is, let me just release and then show you. Now, this charge is not going to move down. Therefore, what does that mean? The physical meaning of this is the external agent of work need to be done to move this negative charge to this other point. Now, the same will happen if I make that charge, or not charge, that particle to be neutral. Now, if I release, there's nothing that is going to happen. Why that is the case is because we have seen that the neutral particle from the chapter 23, when it is in the region of the electric field, it is not getting any influenced by, or it is not influenced by the electric field, like a positive charge or a negative charge. So that's what I basically wanted to show you as far as that is concerned. Now let me just go back to the slides. Right. So that's what I wanted you to see from that simulation. Right. Now, a system consisting of a positive charge from that simulation and an electric field loses electric potential energy when the charge moves in the direction of the field. An electric field does the work on the positive charge when the charge moves in the direction of the electric field. And in comparison to the gravitational field, who does work there? The gravitational field is doing the work. Now, the charge particles gains kinetic energy equal to the potential energy lost by the charge field system. And of course, this is a very good example of conservation of energy. Now, if Q is negative, then the change in U is positive. The change in U, the change in potential energy, is positive. A system consists of a negative charge and an electric field gains potential energy when the charge moves in the direction of the field. In order for a negative charge to move in the direction of the field, an external agent, as I've said, must do positive work on the charge. Right, let me also introduce you to equipotential. Now, for example, consider this figure here. Now, point A is at the lower potential than point A. I mean, point B is at lower. This point B is at lower potential than point A, and point C is also lower at the lower potential than point A. But if we can reverse this electric field, if the field was going to be moving to the left, therefore B and C were going to be at higher potential than A. Now, however, in this case, when the electric field is going in that direction, in your right, the points B and C are at the same potential. Now, why that is the case is because all points in the plane perpendicular to a uniform electric field are at the same electric potential. Now, the name equipotential surfaces is given to any surface consisting of a continuous distribution of points having the same electric potential. Now, I just want us to prove that the potential at B is just the same as potential at C. Now, how can we actually do that? Now, we can just do that. We just want to prove that the potential at B is just the same as the potential at C. And now the only way to do that is to actually to prove that the change in V from A to B is just the same as the change in potential from A to C. Now, how do we do that? Now, let us just start with this one. Now, in this case, the change in potential for V2, the change in potential for A to B, let me just write it in this fashion. We know from the equation that must be the integral E dot D ds. Now, in this case, this is just the dot product of two vectors, and the dot product of two vectors is nothing else but it can just be given as scalar quantities, as the magnitude of that and the magnitude of ds, and then a cosine of an angle between them. Now, in this case, the cosine of an angle between E and ds from moving from A to D is just going to give us this is just going to be minus E, and then the integral ds. The integral ds is nothing else but it's just s. It's just s. It's just that magnitude of that vector s. It's just that magnitude of vector s. Now, that will be times the cosine of an angle between them. Now, from that diagram, what is the cosine of theta? The cosine of theta is nothing else but it's just d divided by s. Now, when you are here, you can just be able to show that the change in the potential there is just given by negative ed. Now, if we can be able to also show that the change in potential for moving from A to C is equal to this, then we will be in a position to say the potential at B is just the same as the potential at C. Now, in that case, everything will just be the same. Now, everything will just be the same, and then I just want to take it from here in solving that problem there. Now, in that case, we are just going to have this minus E, but the cosine between the ds and the electric field is in the same direction. Therefore, the theta is just 0. Now, as a result, you are just going to have 1 for the cosine of 0. Now, the magnitude ds is nothing else. The magnitude ds in this case from A to C is nothing else but it is just d. As a result, we have actually proven because this value here is just the same as this. Therefore, that will imply that the potential at B is just the same as the potential at C. So we have actually proven that the points which are perpendicular to the electric fields are always at the equipotentials. Now, the charged particle in a uniform field, example, suppose that a positive charge is released from rest. When it is released from rest, it means that the VA, when it is moving at the point A, the VA is equal to 0. Is moved in the direction of the electric field. The change in potential is negative. The change in potential is negative, as we have done in the for the previous slides. The change in potential energy is negative. The force and acceleration are in the direction of the field. Now, the conservation of energy can be used to find the final speed of the particle. Right. Now, let us also do the following quick quiz. The labeled points in the figure are on a series of equipotential surfaces associated with an electric field. Rank from greatest to the least the work done by the electric field on the positive charge particle that moves from A to B, and move from B to C, and move from C to D, and then move from D to E. Now, if we have to rank the work done by this. Now, let me just start with the A to B for clarity. Now, from A to B, A and B are just on the same potential. Therefore, there's no work that needs to be done to move that particle from one point to the other. Now, for example, I want you to picture this like, say you have a river, and if this river is so flat like that, and you have point A and you have point B there, will the water flow from point A to B? No, the water is not going to flow from point A to B, because this is just a flat river. However, if I make that river to be something like that, and then I have point A there, and then I have point B here, now will the water be able to flow from point A to B? Yes, the water will then flow from higher potential to lower potential. But if A and B are at the same potential, there will be no flow of water. Now, this is one good example that I want you to always picture the potential as this flow of river. For example, the positive terminal and negative terminal of a battery are totally at different potentials. As a result, that is why there's a flow of electrons from positive to from one side to the other. When you have positive terminal and positive terminal, for example of a river, you are just making that surface to be flat like that, and as a result, there's no flow of electrons from one point to the other. Now, and also let me talk about moving from B to C. Now, if you move from B to C, the change in potential there is just going to be 2, because you are moving from 9 to 7. Now, as a result, or in order to summarize this, if you arrange this in order, this is what you are going to have if you arrange them from greatest to the least in terms of the work done. Now, for moving from B to C, therefore the electric field will just be doing the from B to C, from B to C, the electric potential will just will be decreased by 2 volts, because you are moving from 9 to 7, and then so the electric field will just be performing 2 joules of work for each coulombs of positive charge that should be moving. Now, moving from C to D, the electric potential will decrease by 1, because we are moving from 7 to 6. And now in that case, the electric field will just be doing the work of 1 joule. Now, for A to B, as I've said, there's no work done there. Now, let us also discuss D to E. D to E. Do you see D to E? You are moving from lower to higher. Then that will be the potential will increase by 1 volt. Now, therefore, the field does negative work, negative 1 joule work per unit charge that is going to be moved. Now, in this case, I want you to always remember the previous quick quiz that we have done, so that you can be able to see why is negative, why is positive, why it is increasing, why it is decreasing. Now, therefore, I just want to leave that that for you to figure it out. However, if you still have some problems, then you are free to ask me during our tutorial session. Now let us also do the following quick example for the electric field between two parallel plates of opposite charges. Now these two parallel plates is nothing else but is the capacitor, and that is a chapter that we will be doing after this one. Now a battery has a specific potential difference between its terminal. Establish that the potential difference between the conductors attached to the terminals. A 12 volts battery is connected between two parallel plates as shown in the figure. Now the separation between the plates is just given as 0.30 centimeter. Now there's a prefix there, and we assume the electric field between the plates to be uniform. This assumption is reasonable if the plate separation is small relative to the plate dimensions, and we do not consider the location near the plate edges. Find the magnitude of the electric field between the plates. Now, what I want to emphasize again here is the fact that this is not just the potential. This is not the potential. Why that is the case? Because the positive terminal and negative terminal are not at the same potential. Therefore, as a result, this is the change in potential of this battery is just given as 12 volts. Now, in that case, we know the equation which relates the potential and the electric field as well as the D, as well as the distance moving from A to B. Now, in that case, this is the equation which relates this, and then if you plug everything there, this is what you are going to have. Now, this 10 to the power 2 is coming from the prefix because it was centi. That is what you are going to have for that question. Now, let us also do the following question: motion of a proton in a uniform electric field. Now, suppose that a proton is released from rest at point A, in an uniform electric field that has a magnitude of 8.0 multiplied by 10 to the power 4 volt per meter as shown in the figure. The proton undergoes a displacement of a magnitude d is given by 0.50 meter to point B in the direction of the electric field. Find the speed of the proton after completing the displacement. As I've said earlier on, we just have to use the conservation of energy. The total kinetic energy plus the potential energy must just give us 0. This is the mechanical energy. Now, in this case, the kinetic energy final is just given by this, and then the kinetic energy initial is just given by 0 because this proton was at rest. Now, the change in the potential energy, we know what is the change in potential energy from the previous slides. Now, the change in the potential energy is just given by Q times change in V. Now we know what is Q. Q is a proton, and now we know what is the charge of a proton. It's just E. This is just E change in V. So that is what you are going to see in that equation over here. Now from there, if you rearrange the equations and you solve for V, this is what you are going to have. However, we have to write change in V in terms of E times D because we know the value of E, it is given, and then we also know the D because the D is also given, is the displacement between point A and B. Now, if you rearrange the equation and then you plug the values, this is what you are going to find as your speed of your proton at point B. Right. Now, the potential at the point and the point charge. A positive point charge always radiates the electric field radiates away from the positive charge. Now, in this case, suppose that I have the point at A, and then I also have the point B. Now I can also see that this point A and point B are definitely at different potentials because the distance from there to there is actually not the same as the distance from there to there. In fact, B is at the lower potential compared to A as far as this charge is concerned. Now, if I have to get the change in potential is just given by this equation here. But now if I take a certain vector r and I am going to move from point A to B taking this path, I'm taking this path. Remember, path is not so important. What is very important is this point A and point B. Regardless whether you take this path going to point B, the potential will just be the same. Or you take this path going from A to point B and you move like that and then you come to point B. The potential there will just be the same. It doesn't depend on the path. So for example, say I'm taking this path and then I'm going there to that potential. Now if I take a certain vector R to a certain point along the path, now along that path, now if I know that the displacement, I going there where I'm going to have just that small, I'm going to this particular point of this path, and I call that a small particular path the ds, small segment of that path is ds. Now in that case the unit vector will just be pointing in the same direction of the vector. Now the magnitude here will just be given as dr, and the unit vector and ds will just be making a certain angle called theta. Now in this case, what I want to do, I want to know what is E dot ds. Now what is E, for example, what is the electric field? The electric field, we know it from the chapter 23, is given by this equation. And also, E dot ds can therefore be given, because we know what is the electric field. I can just plug the electric field there and then ds. But what is ds? Ds, the R dot ds is nothing else but it's just the magnitude of unit vector. The magnitude of unit vector multiplied by the magnitude of ds, the cosine of an angle between them, because they form a certain angle theta. Now here you are not seeing the magnitude of unit vector, but it is there because the magnitude of unit vector is just 1. Now in this equation I can also rearrange this equation in terms of the dr. The dr is just given by this. From the soccer tool you will just find that the dr is just given by this equation. Why I have to take it to dr is because I am seeing that the electric field is just given by r squared there, and now this integration must therefore be done with respect to dr. Now in that case I know what is E dot ds. Now I can write E dot ds in terms of this equation that you are seeing here, so that I can easily go back and plug things back to the integral and then do the integration. Now if I do that, plug back to the integration, this is what you are going to have. Now in that case I'm just going to be integrating 1 over r squared dr. Now if you do the integration there, you're just going to have keq divided by r. There's no power 2 here because of the integration. Right, now let me just remind you what is happening there. Now if suppose that I want you to integrate 1 over x squared dx. Now how do you do that integral? That integration is nothing else but it's just 1 over x plus c, because the integration, there are no boundaries of the integration there. But if there were integration, say from a to b, that was just going to make this answer to be like this, where we're going to have a and then b, and then from there you just plug the upper bound of the integration minus the lower bound of the integration. So in that case, this is what you are going to do, or apply the same procedure even in that case. Now if you do that, this is what you are going to have for the change in potential. For the change in potential, this is what you are going to have. Now in this equation, I just want you to see that when you multiply this with the first term inside the bracket, that is actually the potential at point B. At point B. Now when you multiply this term with the second term in your inside the brackets, this is what is the potential at point A. However, as I've said earlier on, we normally choose the potential to be 0 at r is equals to infinity. When r is infinity, then the potential will just be 0. Why that is the case is because if you have the potential as given by, potential is just given by ke and then q divided by r. Now if r goes to infinity, or if r is equals to infinity, if R is equals to infinity, it means that you are going to be dividing this numerator with a very big number. And now if that is the case, then this answer, the potential, can just be taken as 0. That's what it is just saying here. Now that is what you are going to have. Now if we take that potential at RA to be equals to 0 at infinity, therefore we end up with this equation for the potential. And I want to emphasize this, that this is not R square. Please don't confuse it with the electric field. This is not R square. Now this is your potential, right? Good. Now the electric potential is independent of the path between point A and B, as I've shown you. Which path are you going to choose? The potential at point B will just always be the same. Now it is always good to choose a reference point of V is equal to 0. For example, at RA is infinity, then we have chosen the potential to be 0. As a result, then the potential of the system is just given, the potential at a certain point is just given by this equation here. We will also see when we are doing the examples on that. Now, because of the principles of the superposition, because the electric potential due to several point charges is the sum of the potential due to each individual charge. This is another example of the principle of superposition, or superposition principle. Now the sum is, you just add the algebraic sum of the potentials in order to be able to get the potential due to multiple charges at a certain point P, and V is equal to 0 at R is equal to infinity. And this is what I've just been explaining. Now from all this, I just want to remind you that we have seen earlier on that U is just given as Q times V in the previous slides. But now we already know what is V. What is V? Now in terms of V, I want to write V in terms of KE, and then I want to use the capital letter there just for argument's sake. Now in that case, if I plug the value of V there, I will end up with the potential energy as Q times big Q, and then divided by R. And it's not R square here also, right? Now for argument's sake, this is the potential. And what does this mean? This is just the same as it is equivalent to the, say, force, the electric force, when I compare this. And this is comparable to the electric field. Now why am I saying so? The electric field, you only need one charge to be able to get the electric field at a certain point P, and then you only need one charge to get the potential difference at a certain point P. Now you need two charges to get the electric force, but however, for the electric force, this is the square here, and you also need two charges to get the potential. As a result, I can eventually write this. If I want to call this one Q1 and this other one Q2, then this equation can just be given as Q1, Q2 divided by R. Right, that's what I want you to see, that for the electric potential energy, then you will need the two charges as it is shown here. But for the potential, I can be able to calculate the potential at point P only if I know the magnitude of that charge. Right. Now, if two charges are the same signs, U, the potential energy, is positive, and work must be done to bring the charges together. However, if the charges have the opposite signs, U is negative, and the work is done to keep the charges apart. Right. Now, U with multiple charges. Now, if you have multiple charges, for example, you've got 3 charges. All these charges, if you want to calculate the potential, you need to consider the combination of these 2 charges, and the combination of these other 2 charges, and the combination of these other 2 charges, and that will be your total potential energy of the system of these three charges. Right, let us also do the following quick quiz. In the figure, take Q2 to be a negative source charge. Q2 is a negative source charge. And Q1 to be a second charge whose sign can be changed. If Q1 is initially positive and is changed to a charge of the same magnitude but negative, what happens to the potential? Remember the terminology, potential. What happens to V at that position of Q1 due to Q2? Now the potential is not going to be affected by Q1 because the Q1 is not the source charge. The potential will only be affected by the source charge. Now, as a result, C is the correct answer for that. Now, the part 2 of the equation is actually asking for, in the figure, take Q2 to be a negative source charge and Q1 to be a second charge whose sign can be changed. When Q1 is changed from positive to negative, what happens to the potential energy? Which means the potential energy, you need two charges of two charges system. Now, in this case, if we change this Q1 to be negative, therefore, it will be negative times negative. Therefore, the potential energy will just increase. The potential energy will just increase because you will have a positive change in U. Right. Now, let us also do the following example, which states that as shown in the figure, a magnitude of Q1 is just given as this 2.00 microcoulomb is located at the origin, and the Q2 is minus 6.00 microcoulomb is located at x is equals to 0 and y is equal to 3.00 meters. Now the question wants you to find the total electric potential. Good people, once again, electric potential, not potential energy, electric potential due to these charges at point P. Now we can be able to find the potential at point P because we know the distance. We only need this charge and then we need this distance to calculate the potential due to this charge. But for us to get the potential at P due to that charge, we just have to use the theorem of Pythagoras to get this distance because we know this distance and we also know this other distance. Now we just add the algebraic sum of the two and then we end up with the potential at point P. Now in that case, this is what you are going to have. Now your R for this charge is just going to be 5 from the theorem of Pythagoras. Now as a result, the potential at point P is just given by this answer there. Now it is just a negative value from these operations of the additions, because this value is bigger than that other one, therefore you are just going to have a negative sign there. Good. Now the second part of the equation is saying find the change in potential energy of the system of two charges plus a third charge Q3, where Q3 is just 3.00 microcoulomb, as this charge moves from infinity to point P, which means before this charge was here, we already know what is the potential there. Now this charge which is coming here is not going to change the potential at point P from the previous example that we have done. Now we already know what is the potential there. Therefore, what we need to do is to actually calculate the potential energy. Final potential energy is just given by Q3 times the value of that potential at that point P. Now this is what you are going to have. Now the change in potential is nothing else but is the final potential energy minus the initial potential energy. Now in this case, the initial potential energy is just 0. Why that is the case? Because this charge was moved from infinity. Now from infinity, you remember that R as your denominator is going to make everything to be 0 because it's so huge. You divide a certain number with a very big number, that will just be 0. Now in that case, the change in potential energy is just given by this equation there. Right. Now let us also discuss the case of finding the electric field from the potential. Now assume that we start that the field has only the x component, and if the field is having the x component, the electric field in x component is just defined as a negative gradient of the electric potential. Now I am using the ordinary differential equation here because I know that this is only in x. This is only depending on x. But a similar statement may be applied when this is only in y. If it is in y, this is going to be y, and that is going to be y. And if it is z, that is going to be z, and then that is also going to be z. Now, equipotential surfaces must always be perpendicular to electric field lines passing through them. Now, for example, in the case when electric field is going in this direction, now the equipotential lines are these lines which are going down like that. Now, what if you have a positive charge? Now the electric field will always be going in that direction, and now the equipotential lines are everywhere perpendicular to the field's lines. And this can also happen for the dipole. Now for the dipole, the equipotentials are just perpendicular to the electric field at each point. Right. Now, in general, when we have to define the electric potential, if the electric potential or the electric field in terms of the gradient of the potential, now suppose that the electric potential is a function of all three dimensions. Now if it is given that the potential is the function of x and y and z, therefore if the potential, for example, if the potential is just a function of x, it only depends on x, it means that the electric field can just be written as a negative gradient of dv divided by dx. Now this is the ordinary differential equation. It's d because it only depends on x. However, if v is depending on x and y and z, therefore the electric field can just be defined in terms of the ordinary differential equation. For example, in case of x, this is just going to be a partial differential equation, and then that will going to be a partial. And this is actually from your maths class, that if v is a function of more than one variable, therefore the differential equation, it becomes partial. It becomes partial. That's what I wanted you to remember from your maths class. So now in this case, this is what you are going to have for each and every variable. Good. Now let us also do the following quick quiz before we can even pause. Now in a certain region of space, the electric potential is 0 everywhere along the x-axis. From this information, you can conclude that the x component of the electric field in this region is, if the potential is 0, therefore the electric field will also be 0. Now the second part of the equation is saying, suppose that the electric field now is 2 volts everywhere along the x-axis. From this information, you can conclude that the x component of the electric field in this region is, now this is a little bit tricky because, I mean, if it is 2 volts, positive 2 volts everywhere, it means that the potential is constant. Now from the definition of the electric field is just the negative gradient of because this is in x, I will just use the ordinary, and then this is x. Now, if this is constant, therefore the differentiation of a constant is just 0. For example, you remember in your maths class, when you have the function of x is equal to, say, a certain constant, say 2. Now, if I ask you to get the prime of x, you always have 0 there, because this is just a constant. There's no x in this. This is just a constant. So as a result, in this case, if v is constant, for example, it is 2 volts in that case, therefore the electric field will just be 0, just like here. But when you've got this function, say a function of x is just, say, x squared, and then I ask you to get the prime of that is just going to be 2x. Right, so that's what is going to be the answer for that question. Therefore, you are going to have 0 in that case. Right, now I would like to pause here as far as this chapter is concerned, and keep well, and I will see you in the next tutorial session. Bye.